All right, everyone, so we are here today with homework 4.1, solving systems of linear equations. And I'm going to go ahead and get right to it. I am going to do these a couple different ways as we go through this. So my recommendation to you would be to choose the method that you feel works the best and is the most appropriate, and to use that method for yourself. In the case of this first one, we are required to graph this thing. So the way that I'm going to go about that, folks, is I am going to put both of them in slope-intercept form. And I see that this blue one is already set up to be that way. So I'm going to go ahead and graph it the way that I see it. So just a quick reminder of how we graph things using slope and y-intercept. You see that my slope is -3, which is the same as the fraction -3/1. And I see that my y-intercept is -8. When I was doing this one earlier, I actually made a mistake and made the slope 8 and forgot that there was a negative in front of it. So be careful with that negative sign, making sure to catch it. So with the y-intercept of -8, I will start down here. And the slope being -3/1 tells me to go down 3 and to the right 1, which is difficult to do here because I am going to end up off the graph, but I would end up down there with the slope of -3/1. And then, so as you can see, the line is going to be behaving like this. I am going to have to go backwards, which I don't normally like to do. I don't like to go to the left. But instead of going down 3 and to the right 1, I will go up 3 and to the left 1. So up 3 and to the left 1, 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 up 3 and to the left 1. And so I would end up with a line that looks something like this. Okay. And so that's the blue one. We'll call this line the black line. What we've got is we have -5x plus 4y equals 2. I would prefer to set this up in slope-intercept form, so solving it for y to help me see a better picture of what's going on here. So I would add 5x to both sides, and I would have 4y equals 5x plus 2. Then I'll be dividing by 4. And I would have y equals 5/4 x plus 1/2. And it's kind of a pain that we end up with a half there as a y-intercept instead of a whole number, but I suppose it is what it is. And so what we have here now, folks, is we do have a slope of 5/4, which tells me to go up 5 and to the right 4. And we have a y-intercept of 1/2. So I will start right here at 1/2, and I will go up 5 and to the right 4. So I go up to 5.5 and over to 4. I would go up to 10.5 if it was on the grid, but it's not, and to the right 4, so that would be somewhere like floating right there. And then alternatively, I can go down and left instead of up and right. So I will go down 5 and to the left 4, down 5 and to the left 4. And so our black line would look something like this. Now, when we're solving systems of equations, we have 3 options. We either have one solution, which is going to be 2 lines that cross. We have no solution, and I'm actually going to do this a little bit differently. We have one solution, which looks like 2 lines that cross. We will have no solution, which would look like 2 lines that never intersect. They are parallel. And we have what we call infinite solutions, which is really the same line drawn on top of itself. And so in the case of this pair of equations, we do have one solution. It's one place that the lines intersect. It is right there, and it is at the point -2, -2. So this would be an example of a system of linear equations that has one solution, and that one solution can be found at the point -2, -2. All right, moving on to part B, folks, we are asked if each one of those numbers or those ordered pairs is a solution to the system. Let's take a look. So we have straight away out of the gate -2, -2, and we just identified that as being, yes, it is a solution. It is where the two lines cross. Another question we have is the point 70, which is right here, and that is not doing anything with those lines, so that is obviously not a solution. The point 68 comes up and catches the black line right there. But since it only touches one of the two lines, it is not a solution to the system. For it to be a solution to the system, it has to be a place where both lines cross. Lastly, -3,1 catches the blue line right there, but it is not a solution to the system because it does not intersect both lines. All right, folks, that's going to be it for number 1. I'm going to pause my recording and get ready to do number 2. You can pause and take notes at this point if that's something that would be helpful to you. All right, folks, I'm back with number 2. And what we've got in this case is very much like what we had last time, where we have one of these that is already solved for y, and it is y equals -1/2 x plus 1. So I do have a slope of -1/2. I do have a y-intercept of 1. And so I'll go ahead and start at 1 on the y-axis there. My slope says to go down 1 and to the right 2. So down 1 to the right 2. Down 1 to the right 2. Down 1 to the right 2, down 1 to the right 2, down 1 to the right 2. And then alternatively, we can go left and up. So I'll fill those in really quickly. It's helpful for me since I don't have a straight edge because I'm doing this on an iPad. So, and then that is going to be it for the line that is represented by that equation. All right. Now again, just kind of quickly reviewing. If we have a situation where the other line looks like this, it's going to be no solution because the lines are never going to intersect. And if it was the case that our next line laid right on top of the other one, it would be infinite solutions because the lines would be always touching. Let's take a look at the other equation. We'll call it the green one and see what's going to happen with that. So we have -3x plus y equals -6. I'm going to go ahead and solve that for y. So I'll add 3x to both sides. And what we're going to have is y equals 3x minus 6. And so we will, for this one, go ahead and recognize that we have a slope of 3, or 3/1, which tells us to go up 3 and to the right 1. And we have a y-intercept of -6. Be careful to not lose the negative in front of that 6. And so down here at -6 is where we would be, folks. And then our slope again is up 3 and to the right 1. Up 3 and to the right 1. Up 3 to the right 1. Up 3 to the right 1. Up 3 to the right 1. And alternatively, down 3 and to the left 1. So our green line would look something like that. And we can see again that we do, in this case, have one solution, and that one solution is located here at the point 2, 0. So we have, in the case of this problem here, folks, we have one solution. Found at the point 2, 0. Okay, that's going to be it for number 2. I'm going to go ahead and pause here for a moment and give you the opportunity to do the same. All right, folks, we're on to the next. And this time we are not graphing, but instead this time we are solving using a method called substitution. And when we substitute something, what I need you to understand about that is that we are basically saying, hey, if this is equal to y, and I have y somewhere else in the same problem, I can put this in place of y. And so the way that it's going to work in this case is we have one equation that's equal to y. So we're going to take the other equation, 4x plus 3y equals 27. And we are going to replace y in this equation with 3x minus 4. Because 3x minus 4 is equal to y, we can take it and put it in for y right there. So we would have 4x plus 3, and then our y is equal to 3x minus 4. So 3x minus 4 is going to go in place of y, is equal to 27. And so now that we have done that, you can see that we don't have 2 variables in this equation anymore. We only have 1 variable. We have an x. And we do have an x that occurs more than once. There's an x right there, and there's an x right there. But we can take care of that. That's no big deal. What we really need is we need to have 1 variable so that we can solve the equation for the value of that variable. And so that's the purpose of substitution, is to create an equation that instead of having 2 different variables, an x and a y, only has 1 variable, in this case, x. And so we're going to go ahead and solve this darn thing just as we would any other equation now, folks. We'll do the distributive property here. And we will get 4x plus 9x minus 12 equals 27. And on the left, we'll combine like terms. I see that I can combine the 4x and the 9x to get 13x minus 12 equals 27. I'll go ahead and add 12 to both sides. I will get 13x. Oops, that's a terrible looking 3. 13x equals 39. And so I will divide by 13. And I end up with the equation x equals 3. And so now that I have, it is known that x is equal to 3, I can substitute x back into either one of the original equations. And I'm going to, in my case, choose the one that I think looks easier. And for me, the one that looks easier is the y equals 3x minus 4. I could put it into the 4x plus 3y equals 27 as well. I'm going to do both actually to show you that you would get the same result no matter which way you did it. So we're going to take our x equals 3, and keep in mind you only need to do one of these two. I'm only doing both in my case to demonstrate that it will produce the same answer no matter which equation you choose to put it back into. So I'm going to name these. This is equation 1 and this is equation 2. I'm going to put x equals 3 into equation 1, and I'm going to put x equals 3 into equation 2. Again, you'll see that I get the same result in both of them. So I've got y equals 3 times 3, again, because x is 3. I'm substituting that in. And I get y equals 9 minus 4, and y equals 5. Okay, and if I've done everything correctly, with equation 2, I should get the same result. So let's try it. 4 times 3 plus 3y equals 27. I would have 12 plus 3y equals 27. I would need to subtract 12 from both sides. I would get 3y equals 15. I would need to divide by 3. And I would get y equals 5. And so you can see in both cases, it didn't matter which equation I chose to put x equals 3 into, I still ended up with y equals 5. And so in the case of this system, the solution would be found at the point 3, 5. Again, our x value is 3, and our y value is 5. And so if we were to graph this, the way that it would look, just if I was to draw a quick sketch, it would run into, the two lines would run into each other somewhere up there at the point 3, 5. Something like that. Okay, folks, I hope this is helpful. I'm going to move on to part B. And again, remember, when we do substitution, we are basically just saying, hey, this value is the same as something, and so I can replace it with this. Okay, so I'm going to pause there for a moment and give you the opportunity to do so as well, and I'm going to move on. Okay, so here, folks, we have another situation where we're asked to solve using substitution. And what I see here is that in this case, this is equal to y. And so I could take it and put it in for y in this equation. So since it is equal to y in the first equation, equation number 1, it must also be equal to y in equation number 2. And so I'm going to replace y in equation number 2 with 2x plus 1. So what I will get is 2x plus 1 is equal to 4x minus 5. They're both equal to y, so they must be equal to each other. And so what we've got going on here, folks, just quickly simplifying or solving this, we're going to subtract 1 from both sides. I've got 2x equals 4x minus 6. And again, you could solve it differently than I do, and you would end up with the same result. So again, I'll subtract 4x from both sides now. I'll have negative 2x is equal to negative 6. I'll divide by negative 2. And I will end up with x is equal to 3. So my x value is 3, and just like the equation or the system of equations prior, I can put this value of 3 back into either one of them, and I'm going to get the same result. So in my case, I'm going to choose to put x equals 3 into the first one, into equation number 1, because it just looks easier. And so I can replace x in this equation with 3. So I've got y equals 2 times 3 plus 1. Y equals 6 plus 1. Y equals 7. So my solution to this system of equations, folks, is going to be the point 3, 7. And again, if I was to choose equation 2, I should also get 7. In fact, I will do that really quickly just to verify. So equation 2 is y equals 4x minus 5. And I would have y equals 4 times 3 minus 5. Y equals 12 minus 5. Y equals 7. So again, it doesn't matter which equation I choose to put the x value back into, equation 1 or equation 2, I end up with the same result. I'm going to pause for a moment, folks, and give you the opportunity to do the same. And I'm going to move on to the next. All right, everyone, with this one, we are still using substitution. And we are in a situation where we don't have either one of them that has been solved for x or for y. And what a lot of people end up doing is they decide, oh, I'm going to solve for x or I'm going to solve for whatever. My recommendation to you is to always solve for y, just because it's a consistent thing that you can always go back to and just remember, hey, I'm going to solve this for y. I'm going to put it in slope-intercept form. And then you'll have a y value that you can substitute into the other equation. The way that I'm going to choose to do this one, folks, is I'm going to take the 2x equals 12 plus 6y, and I'm going to solve that for y, and then put that in for y in this equation. You could solve the second equation for y instead, you could solve either the first or the second equation for x instead. And now that I actually say that I think that's what I'm going to do, I think I'm going to take this first equation and solve it for x, because it would be very simple to do that. I could just divide by 2, and then I have an x value. So the alternative, again, is you could solve it for y. Either way is going to be okay. And if you're a person that wants consistency and says, no, I'm just always going to solve it for y, that's totally okay to do that. So I get x equals 6 plus 3y as my x value. And so the thing to understand now is I can take this 6 plus 3y and substitute it in for x right there, because the value of x is 6 plus 3y. So I'm going to go ahead and do that with that second equation then. So I've got equation 1, equation 2. I'm going to take equation 2, negative 3x plus 9y equals 12. And I'm going to put that in for x. So now I will have negative 3 times 6 plus 3y plus 9y equals 12. And I'm just going to go through the process of solving this thing for y, now that I have the only variable that I have in this equation is y. So I will have negative 18 plus 9y plus, oops, my bad, that is minus 9y plus 9y equals 12. Okay, so I have negative 18, a negative y and a positive y makes 0 or nothing. And so I have negative 18 equals 12. That feels a little bit strange, doesn't it? And it should, because negative 18 is never going to be equal to 12. And so when we get into a situation with a system like this, folks, what this is telling us is that that is never going to be true. There's no variable anymore. It is a statement that is not true. So this system is going to have what we call no solution. And if we were to graph this, the way that it would end up looking in the graph, again, I've mentioned this previously, is that we would have two lines that would be parallel to each other, and they would never intersect. That's how it would appear graphically. The way that it appears here in the system is that we end up with a statement that is never going to be true, like negative 18 equals 12, and that is an example of no solution. I'll pause here before moving on to the next. All right, and so we're asked to use substitution for this one. I see that 1 is already solved for y, so I'm going to go ahead and take all of this and put it in there for y. So again, I've got equation 1, equation 2. I will take equation 2, negative 5x plus 3y equals negative 9. And I will have negative 5x plus 3 with whatever y is, 5/3 x minus 3 equals negative 9. And what I would do personally in this case, folks, normally is I would multiply everything by 3 to make those fractions go away, or that fraction go away. I do in this case see, though, that when I just do the distributive property here and multiply by 3, that it will make the fraction go away anyway, because 3 is divisible by 3, so I don't need to worry about multiplying everything by 3. If that's something you feel comfortable doing, go for it. So what I'm going to do, folks, is I'm going to have negative 5x plus 15 over 3x minus 9 equals negative 9. I will simplify my fraction there, so I've got negative 5x plus 5x minus 9 equals negative 9. A negative 5x and a positive 5x make 0, so I'm left with negative 9 equals negative 9. Now, up here we had a statement negative 18 equals 12 that was never true. Here we have a statement that negative 9 equals negative 9, and that is always true. So this is an example of an equation that would have infinite solutions. And the way that that would appear on a graph, folks, is we would have a graph that would have two lines on it that are truly laying right on top of each other, just like that. And that would be an example of infinite solutions. So that's how it shows up in an equation and in a graph. I'm going to pause here and give you the opportunity to take notes or do what you need to, and then I will move on. Okay, folks, we are asked to solve these with the method of elimination. And so elimination is really just a fancy way of saying subtraction. I'm not a huge fan of elimination because it seems like a magic trick, but we'll go ahead and do that because that's what we're asked to do. Me personally, I would just continue solving everything using substitution, but we are asked to use elimination, so I will go ahead and do that. The goal in elimination is to create two opposite terms. So like in this case, we have a positive 3y and we have a negative 3y. That is exactly what we're looking for when we do elimination. We want opposite terms. Because what's going to happen with these two equations, equation 1 and equation 2, using the method of elimination, we are going to add these two equations together. And again, it feels very much like a magic trick to me. I've never been a fan of it, but basically what we're going to do, folks, is we're going to say, hey, I'm going to add all the x's, all the y's, and all the constants and see what I get here. So in this case, I would get positive 5x. The negative 3y and the 3y are going to make 0. And I would get 5x equals negative 10. From there, now I only have one variable, so I can divide by 5. And I get an x value of negative 2. It's a faster way to get an x value than using substitution. But again, seems like a magic trick, and I prefer substitution. Just as with substitution, though, we can take our x value and put it back into either equation 1 or equation 2, whichever one we think looks easier, to get our y value. For me, the first one looks easier, so I'm going to choose equation 1. So I will have negative 8 plus 3y, or negative 8x plus 3y equals 7. Negative 2 will go in for x. And I will get 16 plus 3y equals 7. I will subtract 16 from both sides to isolate my y variable. I get 3y equals negative 9. And then lastly, dividing by 3 will give me y equals negative 3. So as far as my solution to the system goes, folks, my x value is negative 2. My y value is negative 3. Those two lines would cross at the point negative 2, negative 3, if I was to graph them. I'm going to pause here for a moment and give you the opportunity to take notes and then move on. Okay, folks, we are back with the next, and we are asked to use elimination with this one as well. What we notice with this one, though, that is different than the one before it, is we do not have any opposite terms. And by opposite terms, I mean that we had the negative 3y and the positive 3y there that were opposite of each other. We do not have that in this case down here. And so what we want to do is we want to create opposite terms. I could choose to make the x's opposite of each other, or I could choose to make the y's opposite of each other. The way we're going to do that is by multiplication. And so I already see that the 3 and the negative 7 are opposite signs, and I'm going to go ahead and capitalize upon that. So I'm going to take equation 1, and I'm going to multiply all of it by 7, which will make 21x. I'm going to take equation 2. I'm going to multiply all of it by 3, which will make a negative 21x. So my eventual goal is going to be to have 21x in the top equation and negative 21x in the bottom equation. So I'm going to go ahead and get to that, folks. So the top equation, everything multiplied by 7, I would get 21x minus 35y equals negative 7. In the bottom equation, if I multiply everything by 3, I would get negative 21x minus 6y equals 48. Now if I do the same as I did previously and I add these two equations up, I'm going to end up with 21x and negative 21x making 0, negative 35y and negative 6 making negative 41y, and negative 7 and 48 making positive 41. Solving for y, if I divide both sides by 41, I end up with y equals 41. Now that I know that y is 41, I can take y equals 41, and put it back into either one of these two equations, equation 1 or equation 2, to find a next value. I think I will choose equation 1. No, I'll choose equation 2. So I will have negative 7x minus 2y equals 16. Again, my y value is 41, so negative 7x minus 2 times 41 equals 16. Simplifying my left side, I get negative 7x minus 82 equals 16. I will add 82 to both sides. And I get negative 7x equals 98. Lastly, folks, I'm going to divide by negative 7. And I'm going to end up with x equals negative 14. So in the case of this one, folks, our solution is going to be xy. Our solution is going to be negative 14, 41. Okay, that's it for this problem. I'm going to pause and give you the opportunity to do so as well, and then I'm going to move on. All right, I'm back with the last two questions for this video. And so what we've got going on is we are asked to solve this system using elimination and state whether it has one solution, no solution, or infinite solutions. So let's go ahead and take a look at what we've got. We have x plus 3y equals 5, and we have negative x minus 3y equals 6. So when we do elimination, what we are doing is we are adding those two equations together. And so let's go ahead and do that. X and negative x makes nothing. 3y and negative 3y make nothing. So on the left side, we have 0. And 5 and 6 makes 11. And 0 equals 11 is never going to be true. So since it is never true, this is an example of a system that has no solution. Ding, no solution. Okay, I'm going to pause there for a moment and then move on. Alrighty, the last one for us today, folks. We have x plus 3y equals 9. And we have negative x minus 3y equals negative 9. So adding those two equations together, I will get x and x makes nothing. 3y and 3y makes nothing. So on the left side, we have 0. And on the right side, 9 and negative 9 makes nothing. So on the right side, we have 0. So 0 equals 0 is always going to be true. And so in the case of this one, folks, we have what we call infinite solutions. There we go. Okay, folks, that's going to be it for this video. A bit of a long one, but is what it is. Hope this was helpful. and I hope you have an awesome day.